Homeostasis describes the body's state of stability and balance. Blood pressure, which is the stress exerted from blood against the walls of blood vessels, is vital for homeostatic regulation. Small medical gauges are often used to determine blood vessel pressure in millimeters of mercury. The result is detailed as two numbers in a division. The first number, or numerator, is the systolic blood pressure that shows how much pressure the blood is forced against the arterial walls whilst the heart beats. The second number, or denominator, is the diastolic blood pressure that displays the pressure applied onto the arterial walls during rest between beats. The American Heart Association recognizes low blood pressure or hypertension at 90/60 and high blood pressure or hypertension at anything over 140/90. Homeostatic systems can adapt in response to varying stimuluses, regulating either a negative feedback loop, one that opposes the stimulus, or a positive feedback loop, one that collaborates with the stimulus. A common feedback loop concerning blood pressure is one involving the medulla oblongata and baroreceptors. This is a negative feedback loop that aids in increasing or decreasing blood pressure with brain signalers in the nervous system, known as action potentials. During elevated blood pressure, baroreceptors become triggered in increasing the basal rate of producing action potential from the stretching of the aorta and carotid arteries, which is where the baroreceptors are located. These action potentials will travel through the vagus and glossopharyngeal nerves to send electrical impulses into the cardioregulatory and vasomotor centers of the medulla oblongata in the brainstem. The cardioregulatory center from the increased stimulation from the baroreceptors will increase parasympathetic stimulation to the heart to reduce the heart rate and decrease sympathetic stimulation to the heart, decreasing heart rate and stroke volume to lower cardiac output. Simultaneously, the vasomotor center decreases sympathetic stimulation to blood vessels, causing vasodilation to reduce systemic vascular resistance and decrease blood flow. This vasodilation, alongside the fall in cardiac output, will regulate the increased blood pressure to a healthy rate. In a decrease of blood pressure, the opposite naturally occurs. Sympathetic stimulation to the heart increases, increasing heart rate and stroke volume to raise cardiac output, while parasympathetic stimulation increases to increase heart rate. The vasomotor center will also increase sympathetic stimulation to the blood, resulting in vasoconstriction to increase SVR and increase blood flow. Just like there are many external factors that can affect blood pressure, there are many ways the body can regulate blood pressure internally as well. The negative feedback loop involving the medulla oblongata and baroreceptors is an example of short-term regulation. The renin-angiotensin-aldosterone system is another systematic example that aids in the long-term regulation of blood pressure and fluid balance. Once a reduction in the renal blood flow is detected, juxtaglomerular cells located in the kidneys secrete enzymatic renin into the bloodstream to convert angiotensinogen secreted by the liver into angiotensin 1. Angiotensin 1 is then changed into angiotensin 2 via angiotensin converting enzymes located in the lungs. Because angiotensin 2 is a peptide, it causes vasoconstriction, which increases the blood pressure. Angiotensin 2 also stimulates the release of hormonal aldosterone from the adrenal cortex, resulting in the reabsorption of water and sodium back into the bloodstream via kidney tubules, which can also increase blood pressure. In the case scenario, 50-year-old nurse Jenny collapsed from dehydration-associated hypertension after a fifth triathlon in scorching heat, even after adjusting her fluid intake. Many factors could have possibly contributed to this. Proper hydration is important for maintaining homeostasis, especially in extreme environments. Temperature rises will normally cause the body to secrete sweat to cool down, resulting in water and salt loss. Jenny seemed to have a severe dehydration. She stayed in the heat for an elongated time and partook vigorous exercises that could have exacerbated her water loss. Her body most likely experienced a homeostatic disruption in which fluid loss was substantial enough to trigger hypertension. Dehydration can result in hypertension as it is ultimately reduced blood volume, which also decreases the blood pressure. Mechanisms regarding blood pressure regulation is highly important in the maintenance of body homeostasis. A lot of systemic processes in our body coordinates with each other, hence vital disruptions in blood pressure mechanisms can be detrimental consequences to our body health and functionalities.